Hello everyone. In this video, I will be discussing on the delays in 8085 microprocessor. What are the different delays and how to generate a delay in a microprocessor, and what is the importance of a delay would be discussed in this video. So, how to generate a delay and how to make up a delay in the program. What is the need of a delay? What actually a delay means, and how to create a delay of your requirement, and how a random delay would be declared. Say random time delay. So let's start our discussion with what actually a delay means. So let's take first of all, a delay is nothing but the amount of time required to process the next instruction. When you go for an instructions, so the first instruction has been completed, and next instruction, how much delay is been there? So delay is nothing but a time gap between uh, one process to the other process. So let's take you are going for an 8085 microprocessor. It has been interfaced to some of the device. So we want any one particular task to be done on your device. Then after a certain delay, we want another task to be done. So this can be accomplished by having a delay between these two tasks. The one task is, let's take I had a 7-segment display. The 7-segment display will be a 8 LEDs will be there. I want to glow the numbers on one 7-segment delay unit. I think you had seen about 7-segment display. So these displays would be visualized. The first, it would be displaying as I want to display the numbers from 1 to 9. After 1, then 2, 3, it goes on after a certain delay. Just like a timer, let's say. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then again, I'm coming back to 1 on a 7-segment display. So this pattern has to be displayed on a 7-segment display. And let's say I want to go for an we say digital clock. I want to design a digital clock. So digital clock, what happens after a 1 second, the second unit would be increased. So it goes on developing the units from what 0 till 60. So after 60, the 1 unit would be increased. So this process I want to go for. Once after 1 second, I want to display 2. After 1 second, I want to display 3. Like that way, I want to proceed. So this can be apparently achieved by having a delay. Delay between 1 and 2 is what? 1 second. So this is one delay. So these delays can be generated. If you want in one way, can generate it. Or sometimes it would be unavoidably delays may be there in the system, obviously. Because each instruction takes a certain amount of time. So one instruction executed, after that one, the next instruction would be executed with certain delay. What is that delay? How much delay? So in the timing diagrams, you have seen that in a timing diagram, you will be having output fetch, memory read, memory write, IO read or IO write, whatever it is, the operations are there. So according to your instruction, whether it is just output fetch instruction or output fetch plus memory read or output fetch plus memory read and memory write with indexing. So this is the direct addressing mode or different addressing mode, the unit of timing required for that instruction will increase. Now, if you consider each clock period is to be zero point 0.2 microseconds and output fetch takes 4 clock cycles. 4 into 0.2 is nothing but 0.8 microseconds. It would be taken to fetch an output. Then memory read may take 3 clock cycles. 3 clock cycles into 0.6. So if it is memory read and memory write, then 3 plus 3, 6. 6 into 0.2, 1.2 plus 0.8. It will take 2 microseconds to execute that particular instruction. One instruction of memory read and memory write. So like that way, delay can be happen. Unavoidably, one instruction executed, next instruction, it looks like all has been randomly generated, but it is not that because it is in microseconds. It could be executed in a shorter delays, very short delays, which can't be observed. So here, the most important thing is that how many bytes instruction is there. P over here indicates bytes, M indicates number of machine cycles, and T indicates number of T states. So these concepts have to be known to you, then only you can have. So here, delay would be equal to number of clock cycles or the number of T states by frequency. How many clock cycles you require? How many you require? Then listen. So let's take this one a simple example. For example, MBI instruction has 7 clock states, and this would be frequency is equal to what? 1 by time period is what? 1 by n. So if your frequency is 5 megahertz, here it is taken an example of 2 megahertz frequency. When you are having a 2 megahertz frequency over here, and number of clock states is 7, then the instruction would take 3.5 microseconds to process this one. So this is about the simple example of a delay which has been there for moving MBI instruction. Now this is one delay loop. How much delay it is making up? How much delay it is making up? So what we are doing is that we are loading the C register with what? FF. Let's take first of all, we will read out this instruction and what meant for this instruction. Why they have this written this instruction. Are they doing any process over here? We'll see. MVI C comma FFH. So we are loading in a constant value FF into C register. Okay, fine. 255 is the value for FF. We are loading in the decrement C. Yeah. Decrement C means 255 minus 1, 254. Jump if not 0 back. So 0 flag won't be set because the C is what? 254. So it will go back. Decrement C. It is just like going on decrement and going back. Then C is becoming what? 0. Then why we have loaded C is equal to F, and then why we are clearing the C? What is the meaning of these three instructions? Yes or not all used. Because if you want to load a value of C as 00, we would have given MVIC, 00H. Then why we have loaded F over here? So here what happens is that when you are loading FF over here, the time required to execute these instructions has gone to uppermost extreme. So when you are going on decrementing this one, going back, it takes some time. And this time is nothing but how many clock states it takes? 4 plus 10, 14 clock states it will take. Going back. And these 14 clock states would be repeated how many times? 255 times. So after 255 times, it will come out of this one. 255 times into 14 into what? Plus this 7 would be also there. Plus 7 into the processor frequency would be the time required to execute this one. So this is called as a delay loop. So you can fix a delay loop with some count value over there. That much count value will be repeated. So this is the total calculation. What we will say the delay loop calculations. T delay is equal to T0 plus TL. T delay is nothing but total delay of the timing diagram. T0 is the delay outside the loop and T is the delay inside the loop. And more T0 or T initial we can say it is the 7 clock states we have seen MVI instruction, and then TL you can say this is the total clock states. This would be that. Now let's take this is one more delay loop using of register phase. Now here, what we can do over here, better going to this same example. If you want to make a required delay, okay, and we doesn't want a delay of whatever the unwanted delay do, it doesn't want we want 1 millisecond delay or 2 millisecond delay. Then how can you make a delay of this one? So what we can do is that, first of all, out of this one, you have seen the total delay is equal to number of states by frequency. So here, when you go for this one, total delay is equal to T0 plus TL. TL is the loop states, how many times it has been repeated. As we have seen, there are 376 states. Initial state is what? 7. And here, how many times you are moving it up, that must be the time. Now, if you want a required 1 millisecond delay, so total delays clock required for 1 millisecond is what? We go to this one. Over here, number of states is equal to delay. Delay is what? 1 millisecond. And here, frequency is what? Frequency is what? Or we can say frequency 1 by 2 megahertz, it would become as zero point 0.5 microseconds. 1 millisecond divided by zero point 0.5 microsecond. It would be what? 2000. 2000 clock states you require. Number of clock states would be equal to what? 2000. Now, how you distribute 2000 clock states? So, initially, out of this 2000 clock states, 7 clock states are being defined for the first instruction. The remaining has to be built up such a way that 14 into the number of how many times this loop has to be repeated to get exactly as 2000 clocks. I mean, there's a 2000 minus 7. And obviously, one more thing you need to mention it over here. When this jump instruction executes, it takes 10 clock states. If it doesn't execute, it takes less clock states. It takes less than 10 clock states. That is the reason. So by this one, we can make a delay of the required time as you require. So overall here, not going in one more type of routine. Here, two loops have been defined. One for B value has been loaded and C value. So here, inner loop and outer loop, this will take larger delays would be there in this one. And it is about 16-bit registers. We can have larger delays for 16-bit. That is not required. If you are having smaller delays, you can go for this one. So this is all about nested loops and all this one. We are not minded. And I hope by this example you're able to know how to make a delay in the program, and you can easily define the delays in the program, and you can write the programs as you require. Thank you. And next video will be covering on stacks. Next delays and subroutines, how to make subroutines and stacks. We will discuss in the next.